Good morning, AP Chemistry. This is going to be the last section of Chapter 6. This is the thermochemistry chapter. Alright, so a couple of background pieces of information. Calorimetry. For a reaction studied under conditions of constant pressure, which we've been doing, and you've got to remember that under constant pressure, the enthalpy change is equal to the heat at constant pressure, which is the one we've been focusing on. Constant volume, it's energy, but we don't do constant volume, so we've been focusing mostly on enthalpy changes. We can use calorimetry and get a direct measurement of enthalpy. Calorimetry is kind of a very vague term. It covers all these styrofoam cup experiments and the heat capacity calculations and stuff like that. So it's kind of a broad term. Not all reactions are that easy to obtain a direct measurement. So for example, the last video we went through Hess's law. Heat of formation is what we're going into next. In the heat of formation are reactions that are slow to react or difficult to study under constant pressure. And for us, heat of formation is more of a plug and chug kind of a thing, because the heat of formation of each individual compound has already been established and is listed in the back of your book. So we're going to put them in the right place and just figure out the enthalpy change of a chemical reaction from the heat of formation of each substance in the reaction. Alright, so standard enthalpy of formation, another way to calculate the enthalpy of a chemical reaction. Standard enthalpy of formation is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard state. And what does standard state mean? Room temperature in 1 atmosphere. The degree symbol indicates the process has been carried out under standard conditions. So the little, when you see this thing here, this means standard states. Alright, standard enthalpies of formation. Standard states are important for the comparison of one substance to another. We can measure only changes in enthalpy and not absolute values of enthalpy. That's why you always have that triangle in front of the enthalpy sign. We can measure enthalpy changes only by performing heat flow experiments, and these include the change in energy during a formation reaction at standard state. Alright, so what are standard states? Compounds. The standard state of a gaseous substance is a pressure of exactly 1 atmosphere. For a pure substance in a condensed state, meaning a liquid or a solid, the standard state is the pure liquid or solid. For a substance present in a solution, the standard state is a concentration of 1 molar exactly. For an element, the standard state of an element is the form in which the element exists under conditions of 1 atmosphere and 25 degrees Celsius. 25 degrees Celsius is room temperature. So periodic table in the room, if the symbol's in black, it's a solid at 25 degrees Celsius and 1 atmosphere. If the symbol is red, it's a gas at 25 degrees and 1 atmosphere. And if it's in blue, it's a liquid at 25 degrees and 1 atmosphere. So if you look at the periodic table next time you're in the room, you'll find that mercury is a liquid at room temperature and 25 degrees Celsius. If it's a compound, you just have to know CO2 is a gas at room temperature. Water is a liquid at room temperature. Hydrochloric acid is a liquid at room temperature. So those are things that you've had previously that you don't realize, though, that's the standard state. Alright, so a change in enthalpy using the heats of formations. The change in enthalpy will be calculated as the heat of formation of the products summed up minus the heat of formation of the reactants summed up. This is basically going to be a plug and chug. Alright, so in order to calculate the change in enthalpy of a chemical reaction, so this is kind of important to get it through your head, of a chemical reaction, we're going to use the heat of formation of each substance in the chemical reaction to calculate the change in enthalpy of the chemical reaction. And it's the chemical reaction will be equal to the summation of the heat of formation of the product substances minus the summation of the heat of formation of the reactant substances. All right, enthalpies of formation. The reactions are written so that the reactants are in their standard states. Enthalpies of formations are always given per 1 mole of product with the product in its standard state. All right, so writing reactions in standard state. This is just writing it, just writing out this reaction. I am going to write out the formation of solid aluminum oxide. So I'm going to write the correct formula for aluminum oxide. All oxides are solids at room temperature, so you don't even need this part. You should remember that. Magnesium oxide is the one you're most familiar with, but all oxides are solids at room temperature. It's the formation of this compound. This is a synthesis reaction. This compound will be made from its constituent elements. Aluminum and oxygen gas form aluminum oxide. States of matter: oxygen is a gas at room temperature. Aluminum is a solid at room temperature. This is aluminum foil. And then you would go ahead and balance it. All right, so this is a balanced reaction, and you would say that the heat of formation of the aluminum oxide is equal to some number. Okay. Now, again, reactions are written that the reactants are in their standard states, which we got. Enthalpies of formation are always given per 1 mole of product. So this enthalpy change will be some number, probably in kilojoules, per 1 mole of product. Right? Well, there's a disconnect between the way the reaction is written and the units of the enthalpy change. The reaction is written so that there are 2 moles of the aluminum oxide, but the heat of formation is for only 1. So we have to manipulate the reaction for it to reflect the heat of formation. Well, that's easy enough to do. I'm going to reduce it by half. So I will get 2 aluminums, solids, plus 3/2 oxygen. This is just a formality, but you have to understand that the reactions are given to reflect 1 mole of product. It's just a manipulation of the reaction to reflect the units for the heat of formation. Alright, so we're going to try it again. The enthalpy of combustion of liquid benzene and delta H of combustion values assume 1 mole of compound is combusted. So again, a chemical reaction, and again, we're going to just write it out. And we are just not calculating anything yet. We are writing the reaction for the combustion of liquid benzene, and we want some number in kilojoules per mole, per 1 mole combustion. Okay, so first thing you got to realize is my chemical reaction is not balanced, so I have to balance it. And how I would balance it would be if I were to balance it appropriately, I'd probably balance it like that and think that was fine if I was just doing my balancing. So if I was in Chapter 3 and I asked you to balance this reaction, that's suitable, that's fine. We're in Chapter 6, which is the thermochemistry chapter. Heats of combustion for a chemical reaction at standard state has to be in kilojoules per 1 mole of combusted substance. Well, I don't have it written to reflect 1 mole. I have it written to reflect 2 moles. So you just have to realize that most of these are going to be written per 1 mole. This is the correct way to write this reaction so that the heat of combustion of the unit, kilojoules per 1 mole, will reflect the reaction. So the reaction correlates to the units. Alright, so what we're going to do is an example here. They've given me a chemical reaction. They're asking me to calculate the enthalpy change of the chemical reaction using the standard enthalpies of formation of each compound or element in the chemical reaction. And I get those from the back of the book, so there's nothing to memorize other than knowing this is another way of calculating enthalpy, other than knowing that you're just going to use a standard list and it's products minus reactants. So this is going to be very super simple. Alright, I am going to write the reaction again so I have it staring me in the face. Alright, a couple of things I want you to write down and to realize. I am going to calculate the enthalpy change of the chemical reaction based on the heat of formation of each substance in the reaction. So I am basically going to go to the back of the book and find the heat of formation of the ammonia gas and the oxygen and the methane and the hydrogen cyanide gas and the water, and I am going to use them to figure out the heat of formation of the actual chemical reaction that these substances are involved in. Alright, and I'm going to say that one more time because it's important for you. Alright, so I'm going to say this one more time because it's really important for you to understand this. It's not hard, but you have to think about it. I am going to use the heat of formation of each substance in this chemical reaction to calculate the enthalpy change of the... So if I go to the back of the book, and keep in mind it's products minus reactants, so I kind of put everything in big brackets. It's the product side first. So for the HCN, it's 2 moles because that's the coefficient, because the heats of formation of HCN is per 1 mole. Well, I don't have 1 mole, I have 2. Alright, so here's what I want you to realize. A couple of things. Thing number 1, this side is all the products. It's products minus reactants. Every heat of formation in the back of the book is given per 1 mole. So for example, my very first one here is the heat of formation of the hydrogen cyanide gas, and it's given to me per 1 mole. Well, I have 2 moles because I have 2 HCN. So my 2 here is the coefficient. I have 6 moles of liquid water. Now be careful because states of matter are important. You will find the heat of formation for gaseous water is different than the heat of formation of liquid water. So you must watch out for the states of matter. The heat of formation for 1 mole of liquid water is a negative 242 kilojoules. Well, I don't have 1 mole. I have 6 according to the balanced chemical reaction. Then minus the reactants. 2 moles of ammonia gas. The heat of formation for 1 mole of ammonia gas is a negative 46 kilojoules per mole. The heat of formation for 2 moles of methane gas will be 2 times the heat of formation of 1 mole of methane gas. Now, take a look at my reactants also. You will notice the lack of the oxygen. So elements are 0 because they're not technically forming from 2 or more other substances. Don't forget, heat of formation, for example, of this guy, which would be, of course, 1/2, 3/2, and 1, is going to be a negative 46 kilojoules per mole. You are forming 1 mole of ammonia. The formation of this ammonia gas is being used to calculate the enthalpy change of the chemical reaction it's involved in. And back to our original problem. Put it in your calculator, or me, I kind of write it all out. But what I get is and you'll notice there are no per mole because mole per mole is for heat of formation. This isn't technically heat of formation. This is a enthalpy change of a chemical reaction. I'm using the heats of formation of the substances in the chemical reaction to calculate the enthalpy change of the chemical reaction. So it's kind of revolves around these two prepositions. So that last line is relatively important. So the enthalpy change of that chemical reaction is a negative 940 kilojoules. It's an exothermic reaction, and I use the heat of formation of each substance in the reaction to determine the enthalpy change of the reaction. Chapter 6 in review, the different ways we calculated enthalpy. That's everything.